interval type 2 fuzzy system and its application. For today, if you have any comment, any question later on, you can just simply drop me an email, or you can visit me in my office, as well as you can find more details information about myself on this website as well. Okay, so today that is a very simple outline, and then so I just break it down into 3 sections. The first one, that is about the introduction about the fuzzy logic systems. I will cover something about the fundamentals of the interval type 2 fuzzy system, which involve the first principle, I mean the working principle of the fuzzy logic system, the interval type 2 fuzzy set, type 1 fuzzy set, as well as the general type 2 fuzzy set. And then I'm going to show some application, this kind of application, which involve the first one, that is the fuzzy rule-based application. That means, according to the name, actually you can see that we are not going to use any model. We just simply use the fuzzy rule and then to perform some application. Another one, that would be the fuzzy model base. According to the title right here, that means we are going to use some model which can help you to design a controller, and then so that we are able to realize some applications. Yeah. Okay. So first essential question, that is, what is fuzzy logic? Okay. So the fuzzy logic, actually, I think that some of you may hear about this this name. Actually, you can find it everywhere. Yeah, you can find it in some engineering application. You can find it in some decision-making sectors. But anyway, that is a kind of technology. We can use it to generate computer intelligence, computational intelligence. So that kind of computational intelligence I'm talking about, that is, we would like to have a machine which is able to generate, for example, to represent human spirit, human knowledge, as well as expertise. That means we would like to have a machine which is going to mimic the behavior of a human being. Yeah? Okay. So think about this kind of knowledge, which involves different kind of characteristics. The first one, that is the information. This information will be, it contains some illness, which contains some uncertainty, as well as some, this kind of uncertainty, which it means that it is a little bit weak to us. I just give you one example. That is, when we consider all these linguistic terms, when we talk about small, medium, large, and so on, and then you will just find out that. Yeah. So you will just find out that when we talk about small, what does it mean by small? Everyone will have different understanding about what small it is. Yeah. Small, for example, this size. To me, it may be small because last year I taught some modules that is 350 people. So I'm going to I taught modules in a very big room. So I consider that this room is small. So I would like to point out that that means small, medium, large. It is related to different contexts. It relates to someone's experience. Yeah. So that means this is a kind of uncertainty. This is a kind of weakness. That means, but anyway, everyone use this term to describe the things, the daily things. Yeah. So this is how it works. That is the way we represent our intelligence. Yeah. Okay. So later on, I will present some structure which can tell you how to use this linguistic variables with that kind of weakness to perform some control tasks or other applications. Yeah. Okay. I'm going to give a few examples about this application. I'm not going to exhaustively to mention all kind of application, just give you a few ideas what we can do using the fuzzy logic system. Yeah, the first thing, that is the control. Yeah, when we talk about the control, we can use it to control of a car, control of a robot, different versions of the robot, bipedal robot, check the robot, as well as when we talk about auto driving, we are able to do the tracking control. When we give a trajectory right here, we are going to design a controller which allows the car to follow this trajectory. When we talk about car suspension system, we are able to say suppress the damping, yeah, so that we are going to give the passenger a very comfort-wide experience. Yeah. Another one that would be the classification. Yeah. So you can see that. So it is not just limited to control. We can extend it to classification. When we talk about classification, for example, this is one application, that is the classification of the biosignal. The biosignals. For example, when we open our hand, close our hand, we are able to determine that what status it is. Yeah. So what status it is? This is open hand. This is closed hand, and that. So we are able to use some learning algorithm to train the physiologic system to tell us what stages it is in. Yeah. Okay. Another one that would be the decision making when we do the investment, and then so we can create a decision maker to tell you what to invest. And then time series prediction, machine learning, when we use the reinforcement learning algorithm, we can use the physiologic system as well. Yeah. So this just gives you some ideas what we can do. Yeah. So physiologic system happens everywhere. Yeah. Okay. Now that would be another realistic example. When we talk about driving, and then so the first one question that would be, if we would like to drive a car and keep a safe distance, okay? So I hope that everyone understands what it means, drive a car and keep a safe distance. But when I ask a little bit deeper, what does it mean by safe? Okay? Everyone will have different meaning on that, subject to your experience, subject to the policy, subject to the rules, right? Okay. But anyway, when we talk about drive a car, everyone will use some rules, okay? Now this one, that is the first rule. If distance is small, then we are going to put the speed as low speed, okay? Everyone should be able to understand this, yeah? But what does it mean by small? What does it mean by low, yeah? But anyway, everyone is going to drive a car to keep a distance like this, okay? I assume that I understand this, yeah? And then the second rule that is very similar. The distance is medium right here. We are going to keep the speed steady. And then the next one, that would be large distance, the speed should be high, okay? We can extend from this point. We are going to talk about if the distance is very small, and then the speed should be very low. If the distance is more or less medium, and then the speed should be more or less steady, something like that, yeah? So we call this as the linguistic rules right here, yeah? So that is the way for us to represent our knowledge, yeah? So we call this as the knowledge base, yeah? Okay, based on this knowledge base, we are going to build up our intelligence, okay? So that means we need to define a few things. That is, what does it mean by small? Whether we are talking about the room or the distance or whatever, yeah? Okay, anyway. Now, once we have the rules, we would like to implement the computational intelligence or computer intelligence right here, okay? So this is the structure of the physiologic system. This physiologic system structure, that is not a new stuff, and then so it was invented or proposed in around 1970, yeah? Okay, but anyway, we still use this kind of structure. You will just find out that this is a block diagram. There's a typo right here, and then you will just find out that we have 4 units. The first one, that is the versifier. The versifier, that is, you can imagine that this rectangle right here, the thing inside, that is our brain, yeah? So that means when we have the input, when we receive an input, the first thing we are going to do is to translate the input into some variables. This variable I'm talking about, that is the linguistic variable. For example, when we talk about driving, okay, when we talk about driving, we are going to use our eyes to capture the information about this distance. That would be the input right here, yeah? So we do not need to know what exact value it is, whether it is 1 meter, 2 meters, or 3 meters, whatever. But anyway, we are sensing the information right here. But in our brain, we are not going to work with numbers. We are going to work with some weakness or linguistic terms, yeah? So the versifier, that is to translate this distance, okay, into, for example, the input that is 3.5 meter, and then so we are going to translate it into small medium, and large. So how do we judge whether this 3.5 meter, that is medium, small, or large? We are going to use the membership function. The membership function is right here. Just to recall that, we have 3 groups. So that's why we have small, medium, and large. That is our database. If we are going to extend the number of groups into 100 groups, and then so we are going to have more membership functions right here. So we try to relate this input, translate into small, medium, and large. That is the way what we do. Input, that is 3.5 meter. Draw a vertical line. We cut across a number of membership functions, the red line, green line, the blue line as well. Take the red line as an example right here. The intercept, that is 0.25. It means that this input 3.5 meter, that is around 25% belong to small, okay? So that is how we measure the contribution of the input to each linguistic term, small, medium, and large. Yeah, so that is the contribution we are going to talk about. Okay, so that means rule 1, the contribution, that is about 25%. Rule 2, that is the medium right here, 83%, and so on. The last one, the contribution made by rule 3, because it cuts across right here, that is 0. That means the contribution made by rule 3, that is 0. Okay. So we combine, we translate the input into the linguistic terms right here, and then we try to relate this information into the rule base to tell how much contribution each rule is going to contributing to the final decision. And now we are going to collect these 2 pieces of information and put it into the fuzzy inference engine. The fuzzy inference engine, that is the decision maker. We are going to make a decision based on our experience developed in these rules as well as the membership function to determine what action we are going to take. Yeah, so that is the reasoning. Yeah, okay. So according to the contribution given by this information, given by the membership functions, it just tells you that. According to rule 1, because it is about 25% of small, so the output right here, the speed, according to the first rule, it should be a little bit low, okay? And then according to the 83% of medium, it just tells you that the output according to this rule, it should be around more steady, okay? And the last one, definitely it is not high, because the contribution made by rule 3, that is 0. Okay, and now we are going to make a decision that is very similar to our mind. Okay, the next step, that is, we would like to generate the action. This action, that is, if the input, that is 3.5, and then the output speed should be a little bit low, more towards steady, but definitely not high. Okay, so to us, at least, get some sense about it. But how do we translate this information into the actuator? Yeah, because we cannot just say our eyes capture this information, processed by our brain, and then we have to translate this information into our limbs, that is the hand as well as the neck, to determine how hard we have to push, step on the accelerator or the brake. Yeah, this information, it does not understood. It does not understand by this actuator. So we need to have the diversifier, which is going to translate this decision into something understood by this actuator. For example, turn this decision into 20 miles per hour, something like that. Yeah. So this is how the fuzzy logic works. But of course, this is just the working principle. How do we really implement that? And then I'm going to talk about that in the next page. In this page, we still stick to this diagram, 4 basic components with these 3 rules as example. Okay. According to the first bit, distance is small, medium, large. I'm going to put it in 3 separate figures right here. Small, that is the membership function, medium, and large. In the previous slide, I just put all of them into one figure, small, medium, large. But now I'm going to expand it into 1, 2, 3 figures. Okay. The same applies to the speed. We are going to talk about the speed is the steady speed as well as the high speed. Okay. Now we stick to the same input. For example, the input 3.5 meter. Draw a vertical line. We obtain exactly the same contribution. 25%, 83%, 0%. Now that is, we process the if part. Calculate the contribution made by the if statement. Now we are going to talk about the consequence. That is the decision made by each rule, and then we are going to aggregate all the rules, the decision together to come up with the final decision right here. Okay. And now we are at this point, the falsification, and then we draw our horizontal line, and then it tells you that how low the speed should be, that low. Okay. How steady the speed that is, that's steady. Okay. So we are going to highlight the gray area. That is the individual decision made by each rule. So we are now at this point making the individual decision by the physics inference engine. And now we are going to combine all these individual decisions to come up with the final output. Okay, that is the way. This axis, y and x axis, actually that is the same of this one. I just simply put it in a separate figure and draw and drag this gray area into this one to represent that. That is the output from the first rule, and then the second rule, and then I'm not quite sure whether you can see that, yeah. But anyway, so put this one and this one together, and then we come up with this gray area. That is the output we obtain. We call this is the fuzzy output. That is the action we are going to take. That represents the decision I mentioned before. That is a little bit low, more towards steady, definitely not high. Yeah. Okay. So we are going to use the defalsification method to translate this output into a numerical output right here. Okay. So that is the more detail about the working principle of this fuzzy logic system. Yeah. But anyway, all this fuzzy logic system, the fuzzy logic system I mentioned right here, that is type 1 fuzzy logic system. In the next step, I'm going to introduce you the concept about the type 2 fuzzy logic. That is the motivation. That is, how do we know that the distance is exactly 3.5? We don't know, because we are not going to use a laser pointer when we're driving and then measure the distance between the cars, right? So we roughly know that this is 3.5, and different people will have different position on the distance. For example, when I take off my glasses, and then the distance, the sense may be different. So the distance may be 3.1, 3.85, 3 point something. So that is a kind of uncertainty. This uncertainty may be due to the error of the sensors. Yeah. Okay. So to deal with this kind of uncertainty, we are going to increase the type of the fuzzy membership function by 1. Actually, we can extend it to type 2, type 3, type 4, and type n. But anyway, when we increase the type number, that is the way for us to handle the uncertainty. Yeah. Okay. And now, the main difference between this diagram compared with the previous one, that is the type reducer. That means the previous system, the previous structure, that is, we only handle type 1 membership function. But now we are going to increase the type number. So that's why we are going to use a type reducer to reduce the type number before we are going to translate the fuzzy output or the fuzzy decision into a numerical value. Yeah. Okay. Anyway, this is the membership function I mentioned before. Now take a look at the membership function right here in the middle. That is something similar to the membership function of the medium. So we have a trapezoid, we have a Gaussian shape. When we draw a line right here, when the distance, that is 3.5, it cuts across this point, everything is fixed. The y value, for example, that is 0.75. Everything is fixed. So that means we assume that the input is correct. No measurement error. But what about, as I mentioned, that now this is roughly 3.5. So we will have something like this. Okay. That means we are talking about this line is shift left and right. That means it will cut across a range of membership function right here. So that means when uncertainty exists, the y values which will be shifting or moving around certain period. So that is the way for us to adjust the uncertainty. Okay. So instead of using the middle membership function, because as I mentioned, when the red line is moving left and right, it will cut across this range. So instead, it means that the y value will be varying around this range. So that is the way for us to capture the uncertainty of the measurement error. Okay. So this is the general type 2 fuzzy set. I introduce one more axis right here. Okay. Now this is the y value, that is this one. The x value, that is this one. Okay. When we have a value, input distance represented by red line, and then, as I said, the y value will be varying within this range. So within this range, and then what would be the value it should be? And then we introduce the second membership function, something like a probability. It just tells you that what would be the probability? It happens to be that value. Okay, according to this shape, it just tells you that the probability is very low. What about the y value at this point? And then the probability is very high. Yeah. So this is the way for us to characterize the uncertainty, and then to give you some idea what would be the y value it will take. Yeah. Okay. Now this is the general type 2 fuzzy set, and then the interval type 2 fuzzy set. The main difference is that instead of using, for example, a Gaussian membership function, we are going to fix the z value right here to be 1. It just tells you that the value of y corresponding to this red line, the probability is always a constant. Okay. But the reason why we are doing that, it is mainly because we would like to reduce the computational complexity when we do the type reduction. If you're going to use a general type 2 fuzzy set, the computational demand is very high. Yeah? So this is just a trade-off. Yeah? Of course, if we are going to reduce this into a constant membership function right here, and then we are going to reduce the express capability of the fuzzy logic system. Yeah? Okay. Anyway, I'm going to give a little bit more remark right here. Yeah? So when we talk about uncertainty, it could be the measurement uncertainty, as I mentioned. Measure the distance between car, whether this is 3.5 or not. Another one, that would be the linguistic term right here. That is, when we use a big, small, medium. So we have to define a range, whether this range is correct or not. Yeah? For example, if I'm going to talk about the distance, that is small, that is within 10 meters. Okay? Maybe you will just say that, okay, to my knowledge, 10 meters belongs to large. Okay? So everyone will have different understanding on this so-called linguistic variable description. Yeah? So this is the linguistic terms uncertainty. Another one, that is the system parameters. Today, I'm going to drive the car. The sensor give me, for example, 3.5. Maybe 1 year later, and then there will be some aging or drifting, and then so the same distance, it gives me another value, something like that. Yeah. So that is the system parameters uncertainty. Okay. So according to this idea, we can extend the type number from 1 to n. When we increase the type number, we are going to enhance the expression capability of the fuzzy logic system. So you can imagine that this fuzzy logic system, that is something like a mathematical model. If we are going to increase the capacity, and then we are able to express more. Yeah? Okay. So try to relate a little bit between type 1 system and type 2 system. Type 2 system can be considered as an infinite number of type 1 system. Yeah? Okay. And now, just very quick summary about what I just mentioned in the previous few minutes. Yeah? Okay. So I mentioned about the fundamental, the working principle of the fuzzy logic system to represent our mind to generate the computational intelligence using the membership function as well as the rule base. Yeah. So you know now how we are able to, how we can compute the intelligence, and then so we have some basic concept about type 1, type 2, and interval type 2 fuzzy membership function. The motivation behind why we need to use the membership function to characterize different linguistic terms. And then we move on to the next section, that is, how do we put this system or to deal with different kind of applications. Yeah. So the first one, that is the fuzzy rule-based application. So when we talk about the fuzzy rule-based system, for example, after driving, we simply put a robot right here to replace a person, and then so what we want to do, that is, we are going to implement the fuzzy logic system, and then this fuzzy logic system will drive the car for ourselves. Yeah. So that means we would like to implement a brain. Okay. So this one, the first one, that is the control of the mobile robot, and then I have done this work many years ago, and then so what we want to do, that is, we have a two-wheeled robot, and this is the source point, this is the target point. We would like to design a controller which is going to drive the robot move from this point to the target point. Yeah. So we use two pieces of information. The first one, that is the error distance d, and then the error angle theta. Yeah. So we are going to construct some rules. You can see that we do not need to have any mathematical models. We do not need mathematics. Yeah. So if you do not like mathematics, that is a good news. Yeah. Okay. Error distance d is small. Okay. This distance, and then error angle, that is small. The angle, error angle, that is the angle difference between the heading angle of the robot and the target. Yeah. So you can imagine that if the distance is small, so that means the robot should move slowly toward the target point in order to avoid overshoot. Yeah. So that is something like you drive a car. If the distance is short, and then you should keep the speed slow. Yeah. And then the angle, that means when you would like to drive the robot toward the target point, so you are going to rotate the robot. Once you rotate the robot, the heading angle points to the target point, you move straight forward. Yeah. So if the angle is small, the rotational force should be small as well. Yeah. So it makes sense, right? Okay. So we are going to have two forces, translational forces. That is the force we are going to apply to the wheels so that the robot is going to move straight forward. And then the rotational force, that is the force we apply to rotate the robot. Yeah. Anyway, we have a number of rules, and then you will just find out that we have some experimental result. Yeah. So this is the P controller. So this one, we use the camera to capture the position of the robot. Yeah. So this is the position of the robot, and then this is the target point of the robot. Sorry. Okay. So the P controller, the P controller, that is a linear controller. We are going to design a controller which can drive the robot from one point to the target point. From the result, you can see that we reach the target yeah, but very quick in the beginning, very slow when we reach the target. And then so we are going to talk about the fuzzy P controller. We use the rule-based system, as I mentioned before. In the beginning, it is very quick. When we close to the target, it is very quick as well. That is because we are going to use, under different conditions, we are going to use different p-value to control the system. Yeah, so that means we achieve a good performance using the cost of implementation. This is just one controller. This is a multiple controller. Which one should be used? It really depends on you. Yeah, whether you would like to have a good performance or whether you would like to have a low-cost controller. Yeah, so we can also use the fuzzy logic system to do the obstacle avoidance. Start from this point. These three guys are the obstacle, and then design the path, and finally reach the target using the fuzzy logic system. We can still apply the fuzzy logic system to implement the decision making. Yeah, so we have two teams to play with each other. One team using the fuzzy logic, and then you guess which team used the fuzzy logic, because one team plays particularly good compared with the naive algorithm. Yeah, okay. So we implement the control algorithm using the fuzzy logic. We implement the fuzzy decision making using the fuzzy logic as well. Yeah. The drug administration, instead of dealing with the control theory, and then so we can use it for, actually it is a kind of control as well, because you can see that we have the PID control. Yeah. So the scenario is that we have a patient. We would like to inject some drugs into the patient to put him or her into sleep. Yeah. Okay. So we have a measurement right here. We would like to keep the measurement to be 52, because I mean the 50, because the 50, that is the perfect status for putting a patient into sleep. Yeah. Anyway, according to this reading, and then so we have a surgeon to play with this equipment to determine how much drugs we are going to inject into the patient right here. Yeah. Okay. And now we would like to use the automated drug administration. Yeah. So this is the structure we propose. If you would like to know the details, just feel free to read these papers. Yeah. So we have a fuzzy inference system to make a decision. That is, we are going to replace the surgeon using a fuzzy logic system, and then so we are going to implement the PID controller. That is the machine right here to determine how much drug we are going to inject into the patient, and then we have the patient model right here. Yeah, and this is the result we obtain. To the left, that is the using the two PID controller. When we talk about the two PID controller, it means that we are using the two linear PID controller, the traditional method, and then to the right, we're using the two interval type 2 fuzzy PID controller. Referring to this diagram, we have the green line right here. It is a kind of tracking control. The blue line, that is the base value, that is the 52, the value we would like to control. So as I mentioned, we would like to pull this line into the green region. Yeah, so you can just see that this is the ideal trajectory we would like the blue line to follow, and then we are going to use the controller to draw the line into this green region. Compare with these two figures, you can see that two methods can do almost the same thing. Yeah, because the blue line is within the green region. The blue line is very close to the green line right here. Yeah, but focus on the overshoot. Yeah. When we use the interval type 2 fuzzy controller, we are able to suppress very well about the overshoot or the undershoot. Yeah, so it just demonstrates that the interval type 2 fuzzy controller has some advantage when we deal with this kind of issue. Yeah. Another application, that is the classification of epilepsy. Yeah. So epilepsy, that is, for example, we are going to measure the brain wave, and then whether we would like to use this brain wave to determine what would be the status of this wave to be. Yeah. So we consider three stages. I'm going to mention that later. But anyway, the idea is capture the wave, and then extract a feature, yeah, so this feature, it means that we do not want to see the overall picture. We would like to just find out some important information from this wave signal, and then so at this point, that important information that is going to represent this wave, yeah, and then we fit this information into the interval type 2 separator machine, yeah. We consider 3 of them, and then finally we are going to use the CAS determiner to determine what status it is. We have 3 cases: non-seizure, pre-seizure, and seizure, yeah. So if we are able to detect the seizure as quick as possible, that means treatment can be applied to the patient, yeah, as quick as possible as well. Anyway, the result is that we compare the result with some traditional classifiers. The first one, that is the proposed interval type 2 separator machine. The second, third, and the fourth, that is the traditional separator machine, and the third, that is the KNN classifier, and then the last one, that is the naive classifier. So you will just see that from the result, it just tells you that we are able to obtain 87.7, which is higher than others, yeah? So it demonstrates the advantages as well. Okay. Now, we are going to move on to from the fuzzy rule-based control, the fuzzy rule-based application to the fuzzy model-based control applications. Yeah. So the idea is something like this: we are going to do the auto-driving, put a robot right here. Before that, we do not need to have a mathematical model. We just simply extract the rules by ourselves according to our experience. Yeah. Now we would like to do a little bit more. So we are going to create a mathematical model for the system, that is the car. We are going to propose a mathematical model for the controller, that is the robot, and then they are going to, we put them together and have some analysis right here. This analysis actually will give you some theory. This theory will tell you how to design the robot so that it works as what we expected. Yeah. So this is the so-called fuzzy model-based control application. We rely on some mathematical model for the design and analysis. Yeah. Okay. So this briefly mentioned about the contribution I have made. Yeah. Okay. The contribution, that is, we create the model, the concept of the fuzzy modeling for the nonlinear system, as well as to propose the structure for the controller in order to form a closed-loop system to realize this task. And then in terms of analysis, and then we also develop the analysis tools to tell you how to design the controller, how to design the system stability of the overall system. And then if you would like to have a look about the details about how it works, and then you are recommended to read these 2 papers as well as the references therein. Yeah. Okay. Anyway, take a look at the applications. The first one, that is a benchmark model inverted pendulum. We use 16 models to represent this system, and then this application, that is about the stabilization. That means we are going to return the pole into the angle 0. Yeah. So at this point, that is a passive point, and then the force applied to the T-joint, that is about this rod. Yeah. So we have a motor right here. The motor, that is to drive the rod left and right in order to generate the force, so that we are able to balance the pole. Yeah. Okay. So this one, that is, we call this is the regulation problem. We would like to make an angle for the pole. Yeah. So now you can see that we keep the angle at degree 10, degree 20, degree 25, 40, and so on. Yeah. If you're going to use the linear PID controller, to my experience, it doesn't work after the angle that is more than 20 or 25. It is mainly because the linear controller, which does not consider the nonlinearity of the system. But when we consider the fuzzy model as well as the fuzzy controller, we address all this nonlinearity, yeah, region by region. Yeah. Okay. Now these 2 applications, actually, I do not consider performance. Yeah, if you really need to consider the performance, and then we can consider this application as well. Yeah, car pole inverted pendulum. we use the same stability condition, but we impose some performance condition there. You can just find out that this candidate balance the pole very quick and return to the center very quick. For others, they can do the same work, balancing the pole and then gradually return to the center line. Yeah. So that is about the performance. That means when you design a controller, you can also, instead of the stability, you can tell the performance as well. Yeah. But there's no free lunch. That means if you would like to have a very quick performance, you need to pay for the control energy. You have to have a much larger control energy to push the car back to the center. Yeah. This was an MSc project I have done sometimes before. That is the implementation of an inverted pendulum, and then so you can see that it is able to balance the robot a little bit. Yeah, but I would mention that it does not last long. Yeah, and then so maybe a few more seconds, and then the robot cannot be balanced. It is mainly because we do not address the uncertainty very well. Yeah. Another one, that is the wind turbine application. Yeah. So when we talk about the wind turbine, especially at this point, yeah, at the moment, so we are going to assembly the fan into the housing using this 128 bolt and nut. Yeah. So how do we maintain the torque to be constant? Yeah, one by one, and then so we are going to do the bolt tightening application right here. Yeah, so in the lab, so we have the bolt tightening tools mounted on the robot hand, and then so this is one of the experiments we have done. We programmed the robot to pick up the bolt and then run along the nut, and then so finally we are able to tighten it. So this interval type 2 physiologic system, that is to control the torque, how much torque we are going to maintain. Yeah. Okay. So anyway, if you would like to know about more details about that, just refer to this paper. Yeah. The next one, that is about the manipulator. Yeah. So we implement the prototype of a manipulator in this form. This is a continuum manipulator, and then so we would like to control the orange part, the tip, move along a trajectory. From this figure, you can just see that the green line, that would be the path we would like the orange tip to follow. The magenta line, that is the actual trajectory the orange tip can follow. So you may see that there would be some error right here. So the result is not perfect, but if you are going to compare the result with some existing state-of-the-art method, and then the error, the checking error, that is much larger. Yeah. So so you can see that the distance actually that is very small, but the thing is that it is very difficult for us to control, to do the tracking control. It is mainly because this is a prototype, and then so when we mention about the prototype, that means there are a lot of imprecision, and then for the model as well as for the for each segment, we are going to implement using the 3D printing. Yeah. So anyway, we come to the conclusion. The conclusion, that is, as I mentioned in the beginning, I present the work into three main sections. The first one, that is to introduce the physiologic system as well as the working principle. Using this working principle as well as the diagrams, we are able to implement the computational intelligence using the physiologic system. And then so to deal with some uncertainty due to measurement error, due to system parameters, and then so we can use the interval type 2 physiologic, the general type 2 fuzzy set as well as the interval type 2 fuzzy set. We can extend this idea from type 1, type 2 to type n. Yeah, and then another one that would be when we use the type 2 fuzzy set, we are able to extend the expression capability of the physiologic system, because type 1 system I mean the type 2 system actually consists of infinite number type 1 system. Yeah? The next one, that is the application. I divide the application into two main sections. The first one, that is the fuzzy rule base. That means we are going to use our knowledge to design the rule base and then to realize the control. The second one, that is we use the mathematical model for the controller as well as the system, so that we come up with some theory which tell you how to design the controller. Yeah? Which method works better? It really depends on the application we consider. Yeah. Okay. So that is the end of my presentation. And if you have any question, and then just feel free to ask me.